Greetings and welcome to the video for problem set number 4 of Chemistry 222, where we'll look at chapter 10 in detail, and I'm glad to have you here. Like the other problem sets before, use a periodic table. I recommend the one at mhchem.org/per-tab. And like the other problem sets before, I want you to self-correct every problem before you turn it in. You should put marks next to the problems that you got right, like one of the self-correct marks there on the right, and also self-correct the problems that you miss. So cross out your old answer, put the right answer in, stuff like that. If you turn in a problem set without any self-correct marks, you will not get full credit. But if you turn in a problem set where every problem has been self-corrected, even if you get every problem wrong, you will still get full credit. So try things. All right, I want you to try things and see how these work out. Should be pretty chill. If you have questions on the material, I encourage you to talk to me. You can also talk to the Avid/LSC Center located above the library on the main MHCC campus. Their website, mhcc.edu/avid. That group offers free tutoring in chemistry to you as an MHCC student, so I encourage you to check them out. They're pretty cool people. Okay, so without further ado, let's get into the problem set and see what this chapter has to offer. Intermolecular forces are literally the forces between molecules in a sample of substance. And intermolecular forces are really helpful when you think about transitions from solids to liquids, liquids to gases, or any other combination thereof. For example, liquids to solids, etc. When you have a liquid and you're turning it into a gas, you must overcome the intermolecular forces in that sample in order for the liquid to be turned into a gas. So really what I'm basically asking you in these questions is, what kind of intermolecular forces are there in the liquid phase? Because the only way that you could turn these liquids into a gas is by overcoming their intermolecular forces. So when you're doing these kind of problems, all right, most of them basically come down to polarity. Is something polar or is something non-polar? And CO2, if you don't remember, you can actually draw out a Lewis structure. It's carbon in the middle of two double bond O's. CO2 is a non-polar molecule. And if something is non-polar, then the intermolecular force working on it is called induced dipole, induced dipole. And a lot of times I will abbreviate that as IDID because that's way too many syllables for me. These forces are sometimes called London forces or dispersion forces, even sometimes Van der Waals forces. They're so weak that honestly I think nobody really cares that much, which is terrible. But anyway, I will refer to them as the IDID, induced dipole force. So any non-polar substance that becomes a gas, you'd have to overcome the induced dipole forces. Now the next one, CHCl3, if you draw the Lewis structure, it's a tetrahedral carbon. There are 3 Cl's and a hydrogen. So not everything is the same around the tetrahedral carbon. That means that molecule is going to be polar. Most of the time, polar molecules imply that the intermolecular force is referred to as dipole-dipole. Dipole-dipole is a stronger force than the IDID forces, and it's the general force that's happening when you have a polar molecule. But there is one exception. On the next molecule, C, which is ammonia, the nitrogen, if you draw out its Lewis structure, the nitrogen has a lone pair. So that's a tetrahedral nitrogen. So that would be a polar molecule, and initially you'd say DD, dipole-dipole. However, if you have a hydrogen connected to a nitrogen, or an oxygen, or a fluorine, it gets like a supercharged version of dipole-dipole. And it's so much stronger that it actually gets its own name. And if you remember from lecture, this is called the hydrogen bonding force. So H connected to N, O, or F gives it like super polarity. Okay, it's not just normal dipole-dipole. You actually give it its own name, which is hydrogen bonding. It's a much stronger form of dipole-dipole, and there's lots of interesting effects that happen. Now on D, it feels initially like it could be non-polar, like sulfur in a tetrahedral set of chlorines. But if you took the time to draw the Lewis structure, you're going to see there's actually a lone pair on that sulfur. So this molecule is not non-polar. It's actually a polar molecule. There are no hydrogens. We don't have to worry about hydrogen bonding. This one's going to be dipole-dipole. Here's the structure itself. Again, initially you might be saying, oh yeah, tetrahedral sulfur, non-polar. No. This is actually a trigonal bipyramid with a seesaw molecular geometry. It is quite polar. This is just a little reminder that's really, really good idea to draw the Lewis structures if you're uncertain. Now, E and F have a part at the beginning and a part in parentheses. And the part in parentheses is the solvent. And the part outside of the solvent, if you will, is like the solute. So in the first one there, iodine and methanol, iodine is the solute and methanol is the solvent. This is a solution. And in the next problem set, we'll talk more about solutions. But for right now, think about the polarity of both iodine and methanol. So iodine is nonpolar, just I and I. It would be induced dipole if it was by itself. Methanol, CH3OH, is polar. It even has hydrogen bonds. It's got that almost magical OH bond. So it's at least polar, and iodine is nonpolar. So if you have something polar and something nonpolar, like you have right here, this is the so-called dipole-induced dipole force. You have something polar and something nonpolar. The iodine is nonpolar. The methanol is super polar. It's hydrogen bonded, but that's not important here. If these two come together, and they do, the dipole-induced dipole force is what's happening. Dipole-dipole is stronger than induced dipole-induced dipole. Dipole-induced dipole force is kind of between the two of them. In the last one, you have an ion, a sodium ion, and you have aqueous, which is water, and water is very polar, hydrogen bonded even, so you'd think of it as something that's polar. If you have something ionic with something that's polar, i.e. with a dipole, this is referred to as the ion dipole force, and the ion dipole force is very strong. It actually breaks up NaCl when it's with water, breaks them into the ions. Ion dipole force is nothing to mess around with. So notice here how we looked at polarity and types of bonds to figure out these different names. The strengths are really important, but the first thing I want you to do is just become familiar with the name so that you know what's going on. Rank the following in order of increasing intermolecular force strength, and at 25 degrees Celsius and 1 atmosphere, which exists as gases and which is liquids. Okay, there's a couple ways to do this problem, all right? But one way to do it would be to go through and find the intermolecular forces on each one of these substances. The first one is propane, an alkane, and the alkanes are basically just a bunch of carbons in a row. And although not totally nonpolar, people usually consider the alkanes to be pretty nonpolar. So for A, I'd probably say that this is induced dipole working on it. It's nonpolar, all right? The second compound is ethanol. Ethanol, like all the alcohols, has an OH. So this means that ethanol is not just polar. This one actually has the hydrogen bonds working on it, okay? So ethanol has hydrogen bonds. The next one, helium, all right? Helium is the most nonpolar, I would argue, of all substances. It's only an atom, and a very small atom at that. Very difficult to induce a dipole on. So helium, you'd say, is induced dipole. And water, which is HOH, has very strong hydrogen bonds, like we saw in lecture. So from the structure of water, it's got OH, that's hydrogen bonds, very strong. So notice here how A and C are both induced dipole, and B and D are both hydrogen bonds. So you've got quite a gap there in strength. Induced dipole, one of the weakest, and hydrogen bonds, one of the strongest, all right? So if you had to guess, just off the top of your head, I'd say that A and C were gases, and B and D with stronger intermolecular forces would be liquids. But you can do better than that. all of these substances I'm hoping are somewhat common to you. The first one is actually propane, and propane is an active ingredient in barbecues, and it's a gas. All right, you buy it in those little containers and stuff like that. B, ethanol is drinking alcohol. All right, and just say no, kids. I'm not encouraging you to start drinking. Well, maybe after learning this stuff you'd want to, but Prof back on. Anyway, seriously, don't start drinking just for this problem. But anyway, it's drinking alcohol. It's a liquid. All right, so B is a liquid. Helium is what's in balloons at birthday parties. Of course, that's a gas. And water, you've probably had today already. It's a liquid normally. So that's another way to see which ones are liquid and gases. You can also look them up in the all-powerful Google if you'd like to, and that's fine. So again, summarizing up here, the intermolecular force, you just go through and figure them out. You've got 2 hydrogen bonded and 2 induced dipole. So that automatically says, probably the induced dipole are going to be gases because they're easier to get into the gas phase. The other ones will be liquid, and that's totally what it is. Now, I did use the all-powerful Google, and I looked up the boiling points. Helium starts being a gas at 4.2 Kelvin. So like in space, all right, it's already a gas. It's just crazy. It's a gas basically everywhere. Propane is a gas too. Its boiling point is -42. So at room temperature, roughly 20-25 degrees Celsius, you bet it's going to be gas. Water and ethanol are both liquids. All right, water you get from the tap. Ethanol is drinking alcohol. And again, don't have to start drinking alcohol just for this class unless you want to. Oh, joy. Helium is a weaker intermolecular force because it's smaller. As you have more atoms, it becomes easier. It becomes a little bit more hard to get it to go into the gas phase. So that's why propane is a little bit harder to get into the gas phase than helium. And water has 2 OHs on it, while ethanol has just 1 OH. So water has stronger intermolecular forces. The enthalpy of vaporization, which is the energy required to turn a liquid into a gas, by the way, the enthalpy of vaporization for mercury, 59.11 kilojoules per mole. What quantity of heat is required to vaporize 0.500 milliliters of mercury at 357 degrees Celsius, its normal boiling point? And the density of mercury, 13.6 grams per milliliter. At this point in the problem set, you might be thinking like, blah, 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 blah. I can't see straight. I'm sick of these problems and stuff, and I totally understand. So let me try and share a hint with you. A lot of times in chemistry and physics, all right, you can literally put the units together, canceling them out, moving on to get the right answer. So check this out. Let's say that you really are just bleary-eyed, you can't see straight. Well, here's a milliliter and here's a milliliter. So if you multiply milliliters by grams per milliliter, the milliliters will go away and you'll have just grams. Well, you've also got a mole up here. And because chemists are obsessed with the periodic table, and I put myself in that category big time, you can look up the molar mass of mercury. Mercury is 200.592 grams per mole. But anyway, that will allow you to turn the gram that you have left here into the moles. And then once you have moles, you can multiply it by this 59.11. You'll get so many kilojoules. And heat is a value of kilojoules. That's what you measure it. So notice how I don't know anything about what's happening in the problem. I'm literally putting the units together, and bam, that's the right answer. That's literally what you do. So here's the steps I just went through. Milliliters times grams per milliliter, milliliters cancel out. Grams times the molar mass of mercury, 200 or so grams per mole, the grams cancel out. Moles times kilojoules per mole, moles are out of here, kilojoules are left, 3 sig figs because 0.500 and 13.6 were both 3, 2.00 kilojoules. And that is the answer. So notice that you really didn't have to know anything about this problem, which is kind of funky, but to get the right answer. Now, what this 2 kilojoule number is, that's the energy required to convert half of a milliliter of mercury into the gas phase. It's endothermic because liquid to gas transitions are always endothermic. It takes energy to make it happen. But notice you didn't have to do that. We didn't use 357 degrees Celsius at all. That's just the temperature at which this transition happens. All right, so it never really popped in here. And remember, like with all of these thermodynamic things, if you wanted to turn half a milliliter equivalent of the gas into a liquid, it would be the opposite process. You'd put a negative 2.00 kilojoules there. Pretty cool. So again, this works a lot more often than I give it credit for in both chemistry and physics. Just something to keep in mind if you ever run into a roadblock. One more thing. Liquid to gas is always going to be endothermic, as well as solid to liquid and solid to gas, because you're having to break intermolecular forces. On the other hand, if you go gas to liquid, liquid to solid, even gas to solid, those are always going to be exothermic. That little hint right there will help you in problem set number 5. So just keep that in the back of your mind, as if you had nothing else to do with your mind or anything like that right now. And again, following the units works really well on a lot of these problems. Use the figure on the right to answer the following questions. And it says, what's the equilibrium vapor pressure of diethyl ether at room temperature, 20 degrees Celsius? Then it says, place diethyl ether, ethanol, and water in order of increasing intermolecular forces. And finally, if the pressure in the flask is 400 millimeters of mercury and the temperature is 40 degrees Celsius, which of the 3 compounds are liquids and which are gases? Okay, so that graph shows vapor pressure curves. And notice that they are all curves. You can see that the temperature is on the x-axis and the pressure, which is the vapor pressure really, is on the y-axis. All of those curves, the vapor pressure increases as temperature gets larger. So you have more pressure as temperature goes up. So the first question says, what's the equilibrium vapor pressure of diethyl ether at about 20 degrees Celsius? No problem. What I would do for this problem is I would literally just go straight up to where you get to the diethyl ether curve. And that's the red line. That's the first curve. Then if you literally go over to the y-axis, that will tell you what the vapor pressure is as that temperature. Looks to be about 400 millimeters of mercury to me. So literally it's that simple. You just look at the graph to see what's happening. Second one, place diethyl ether, ethanol, and water in an order of increasing intermolecular forces. Well, if you look at the structures there, diethyl ether has an oxygen in the middle. And like we've done with all the Lewis structures this term, oxygen almost always has 2 lone pairs. And that's why you're seeing that kind of bent molecular geometry between the oxygen and the ether or ethyl on the left and the ethyl on the right. So diethyl ether we would say is polar. All right, the oxygen makes it polar. Ethanol, the next one to the right, has an OH. And OH means it's not just polar, it's actually hydrogen bonded. So ethanol is a hydrogen bond. And then water on the far right has not just one OH, but actually 2 OHs. So water is like supercharged hydrogen bonding. It's even more supercharged than regular hydrogen bonding, I guess. So anyway, those curves are actually in the order of increasing intermolecular forces. Diethyl ether is first. It has the weakest dipole-dipole force in this list. Ethanol is next with 1 hydrogen bonding, and then with water you have 2 sources of OH. So there I called it super hydrogen bonding. Oh, that works. It's like a stronger version of hydrogen bonding. The last question, it says, if the pressure in a flask is 400 millimeters of mercury and the temperature is 40 degrees, which of the compounds are liquids and gases? So here's what I would do for this problem. I would start at a pressure of 400 millimeters, and I would literally go over to where the temperature is 40 degrees. So I'm just going to take my little line, bam, it's crossing the diethyl ether line. It's going to stop right there. So that point is about 400 millimeters of mercury and 40 degrees Celsius. We went through the diethyl ether line, so that means that diethyl ether now has turned into a gas. On the other hand, ethanol and water, we haven't gone through their curves. We would need warmer temperatures to make those liquids turn into gas. So of the 3, only diethyl ether is a gas. Ethanol and water are still in the liquid phase at those set of conditions. So you can see how this stuff works and how vapor pressure curves can be really helpful when you want to take liquids to gases, stuff like that. Answer each of the following question with increases, decreases, or does not change. If the intermolecular forces in a liquid increase, the normal boiling point of the liquid increases. If you look back at that graph on the last page, the intermolecular forces went from weak diethyl ether to the strongest water, and the normal boiling point, the temperature at which a liquid boils at 1 atmosphere in pressure, it was getting larger. So diethyl ether had the smallest boiling point, ethanol was in the middle, and water was the highest. So intermolecular forces go up, the normal boiling point of the liquid goes up. B, if the intermolecular forces in a liquid decrease, what happens to the vapor pressure? Okay, well, this is another good question. If the forces holding the liquid molecules together aren't as strong, and that's what it means to have weaker intermolecular forces, if they can't hold on to each other that strong, then that means your vapor pressure is actually going to go up. It's going to increase. The forces are holding it less tightly together, if you will, so you're going to have more vapor pressure. Vapor pressure goes up as intermolecular forces go down. C, if the surface area of a liquid decreases, the vapor pressure, well, this is kind of an interesting one that maybe you hadn't thought about, but pressure is force over area. This is stepping our foot into physics here a little bit, but pressure is part force and part area. But the amount of pressure does depend on the area and the force and stuff like that. If you just are decreasing the area, then you're not going to have as much force either. The vapor pressure, if the surface area decreases, stays the same. And what this means is that you can have like a little tiny beaker of water, or you can have like Lake Michigan amount of water, all right? As long as the temperature is the same and they're relatively the same liquid, it shouldn't make any difference. The vapor pressure should be the same above both of them, your little water and also Lake Michigan. Finally, if the temperature increases, the vapor pressure will definitely increase as well. All of those were curves going up. So as temperature went to the right, the x-axis, that means that the vapor pressure also went up as well. We're going to split this one into part 1 and part 2. Look at the xenon phase diagram on the right. And again, all phase diagrams have like a solid, liquid, and a gas phase to them. And you can see how the solid is kind of like to the left, the gas is kind of to the right. And if you use your imagination a little bit, the liquid gas interface there is kind of like a top part of a Y, while the solid gas is the bottom part. The liquid's kind of in the middle of the Y, if you will. But anyway, phase diagrams like this are just more expanded versions of the vapor pressure curves we saw in question 1. If you took just the liquid gas interface, it's got a little bit of a curve. That's what we were looking at back there in question number 1. So phase diagrams are just more complete versions, descriptions of the different compounds. So let's see how this works. In what phase is the xenon found at room temperature and 1 atmosphere of pressure? Well, 1 atmosphere of pressure is definitely on this graph. It's right there. But if you look at those temperatures, the hottest temperature minus 105. So, whoa, that's pretty cold. So you can imagine if you're like a xenon sample and you start off here at negative 125, where it's a solid at 1 atmosphere, you'll go over here to the place where it turns to a liquid, and then to the place where it turns to the gas, and you'll just keep on going on that curve quite a ways, because room temperature is like 25-ish degrees Celsius. We've already went solid to liquid and liquid to gas. Xenon is going to be a gas. And this kind of makes sense if you have a periodic table with the phases of matter on it. All of the right-hand column, those are the noble gases. They are gases, all right? So xenon, one of the noble gases, had better be a gas at room temperature, or else we'll have to redo our periodic table. Not the first time, not the last time, but anyway, it is a gas. Good to go. B, if the pressure is 0.75 atmospheres and the temperature is minus 114, in what phase does that substance exist? Okay, well, 0.75 atmospheres would be right about there, halfway between 1 and 0.5, and minus 114 would be right about here. So you kind of want to make like an intercept. You want to see where those two lines come together. And you can see even by my cheesy lines, they're going to be right there at that liquid interface. So I would argue that on B, that's going to be a liquid at 0.75 atmospheres and minus 114 degrees Celsius. C, if you measure the vapor pressure of a liquid sample and you find it to be 380 millimeters of mercury, what is the temperature of the liquid phase? Okay, 380 millimeters of mercury, we need to convert to atmospheres. So 380 divided by 760 millimeters of mercury per atmosphere, that actually comes out to be half of an atmosphere. So 380 millimeters of mercury is actually half of an atmosphere. And this question says if we have a liquid at half of an atmosphere, what's the approximate temperature? So again, what I would do is I would just go over on the graph until you get somewhere here in the liquid phase. And I would go down from there. And again, this isn't the world's best graph by anything. It looks to me like minus 118, maybe minus 119, maybe minus 117. Something in that range would be totally fine. If you interpreted it a little different, minus 116, it's not the end of the world. The goal of this problem, of course, is to get you to see how to read the phase diagrams. And that's what this is all about. D, what's the vapor pressure of the solid at minus 122 Celsius? Now, normally we don't think about solids as having vapor pressure. Usually the liquids we're more worried about vapor pressure. But if you are at the place where solid goes directly to gas, you will have a vapor pressure of the solid. So in this problem, you want to go to minus 122 Celsius. And that looks like it's right about there on the x-axis. Then to figure out the vapor pressure, you just go up to the curve and then you go over to this side. And again, this isn't the world's best graph or anything like that. It looks like it's about 0.2 atmospheres, 0.25 atmospheres. Whatever number you think that is totally fine. But again, you do see here that solids have a vapor pressure as well. And when solids turn into gases, you have to have vapor pressure, be external pressure, etc., etc. Part E, it says which phase is denser, solid or liquid? Okay, and this is a good question. This is kind of a hidden thing of phase diagrams. Now in Zenon's diagram there, if you look at the solid liquid line, that line has a positive slope, i.e. the solid liquid line, the kind of brownish line there, it's increasing up and to the right. So positive slopes between solid and liquid means that the solid phase is actually more dense than the liquid phase. So anytime you see a solid liquid positive slope line, and again, that's that one right there, that means the solid phase is going to be more dense than the liquid phase. What that means is that if you had solid xenon ice cubes and you put it in liquid xenon, all right, the ice cubes would totally sink to the bottom, all right? They are more dense than the liquid phase. Solids usually will be more dense than the liquid phase. But the reason I bring this up is, of course, about water, because water, solid ice, floats on liquid water. And that's really amazing. That's because liquid water is more dense than solid ice water. And that's just so wild. Here's another example. This is another positive slope solid liquid line. This is for oxygen, O2. And you can see that because it's a positive slope between that solid and liquid, i.e. again, this part right here, that means the solid is more dense than the liquid. And honestly, if you have to guess, most of the time for most substances, that's the way it's going to roll. However, water is one of the few exceptions, not the only exception, but one of the few exceptions. Check out this solid liquid line. See how it's kind of increasing in the opposite way, kind of up and to the left? That means it has a negative slope. And in those cases, the liquid density is more dense than the solid density. So the next time you see an ice cube float on liquid water, it's pretty cool. It's pretty rare. You know now that the slope of the solid liquid line is negative, woohoo! But it's more just kind of neat to think about that this substance we take for granted is actually kind of unique. Most compounds have a positive slope, which means the solid sinks in the liquid, but not liquid water. The specific heat capacity of silver, 0.235 joules per gram Kelvin, and a melting point of 962, and a heat of fusion of 11.3 kilojoules per mole. What quantity in heat is required to change 5 grams of silver from a solid at 25 degrees Celsius to a liquid at 962 Celsius? Okay, I want you to visualize what's happening here first. You're starting with 5 grams of silver, which is a solid, at about room temperature, 25 degrees Celsius. And we're going to do 2 things to it in this problem. First, we're going to heat the solid silver from 25 degrees Celsius to 962 Celsius. That's going to be a Q equals MC delta T. And we looked at these back in Chapter 5 of Chem 221. And if this doesn't ring a bell, I encourage you to go back and check out Chapter 5 of Chemistry 221. Same textbook, all that kind of stuff. In Q equals MC delta T, you need that C, that heat capacity, and that's what that number is right there. So the first part is just to figure out the heat required to heat the sample up from 25 to 962. But we're going to do something different to it as well. We're also going to take that solid and turn it into a liquid at the boiling point at 960, or melting point, excuse me, 962 degrees Celsius. Now this part is what I called in Chapter 5 a mass, quote unquote, times a heat of something, quote unquote. The heat of something here is, no surprise, heat of fusion. That's the energy required to melt a solid. So we're going to take that number and the amount of silver we have and figure out how much energy it takes to turn solids into liquids. Anytime you're heating a sample, anytime you're going solid to liquid or liquid to gas or solid to gas for that matter, gonna be an endothermic value. And endothermic means it's gonna be a positive number, okay? So this problem, we're gonna have basically 2 parts. One to heat the solid, the other one to melt the solid. And we're gonna add those 2 parts together to give the overall energy. Sometimes I like to use this kind of system. It's like a number line. On the x-axis there, if you will, we're starting at 25 Celsius and we're going up to 962 first. That's going to be this Q solid I'm calling it here, that's the MC delta T in order to get the solid to the melting temperature of 962. But then there's going to be a second part, which here I called Q melting, and that's the mass, quote unquote, because you never know if mass is going to be grams or moles or whatever, and then it's going to be multiplied by the heat of something. And in this case, it's the heat of fusion. Now notice that the temperature does not change, but we are changing the solid to a liquid with this value. And then the final answer will be adding those 2 Q's together, and that'll give us the total energy in joules, kilojoules, whatever. All right, so let's look at the math. 5 grams of silver is all we have. So Q solid here is going to be 5 grams of silver times the heat capacity of silver times the delta T. Now I threw in the Kelvin values because maybe some of you did that. But if you remember from Chem 221, you can also use the Celsius values. A delta T in Kelvin is the same as a delta T in degrees Celsius. So if you put 962 minus 25 right there, you're going to get the same number. It's no big deal. And when you do that, the value here comes out to be 1.10 times 10 to the third joules. It's a positive endothermic energy because we're heating the solid from about room temperature to the melting point. The second part of this problem is going to be figuring out the energy required to actually melt the solid. And that's when we're going to use that 11.3 kilojoules per mole. Now, there's different ways to do this problem. What I did here is I took the 5 grams again, and I turned it into moles. So silver on the periodic table is about 107.9 grams per mole. And then the heat of fusion number there, it's 1 mole is 11.3 kilojoules. And that just says that to melt 1 mole of silver, it takes 11.3 kilojoules of energy. Now, because the first number was in joules, I'm going to turn the kilojoules back into joules. I'm going to multiply by 1,000 joules per kilojoule, and you can see it's 5.24 times 10 to the second joules. So the first number, Q solid, that was the energy to heat the solid to the melting point. And then Q melting, that number there, that's the energy required to actually turn the solid silver into a liquid. So the total energy change will just be the sum of those two numbers, and that comes out to be 1.62 times 10 to the third joules. Because it's a positive Q, that means it's endothermic. You have to add energy to make this happen. Cool. Now, one more quick reminder. If you wanted to know the energy to take 5 grams of liquid silver at 962 and turn it back into a solid at 25, you would basically have the opposite of the Q solid we calculated earlier and the opposite of the Q melting. You'd have the opposite of Q solid because your delta T values would change. Instead of having, for example, 962 minus 25, you would have 25 minus 962. You're flipping final and initial. So you'd end up with a negative 1.10 times 10 to the third. For the Q melting, all right, everything would be the same, grams to moles, kilojoules to joules, but the heat of fusion is for taking a solid and turning it into a liquid. If you're going to turn a liquid into a solid, you would just have to put a negative number in front of it. So you'd still end up with a negative 5.24 times 10 to the second. Fusion is just for solid to liquid, but you want, in this hypothetical example, liquid to solid. So the overall energy, the overall Q, would be negative 1.62 times 10 to the third joules. Remember, in thermodynamics, a lot of times if something is endothermic in one direction, it's exothermic in the other direction. Same magnitude, but different sign. Tungsten crystallizes in the unit cell shown there in the picture. What type of unit cell is it? How many tungsten atoms? And if the edge is 316.5 picometers, what's the radius of a tungsten atom? Okay, if you look at that unit cell, and you remember the discussion we had of unit cells back in the lecture notes, you've got the corner atoms in each of the 8 corners in the unit cell, but you also have one smack in the middle of the unit cell, in the body of the cell. So this unit cell is referred to as a body-centered cubic, BCC. The corner atoms plus the one in the middle means it's going to be a body-centered cubic. Now, in a body-centered cubic, whether it's tungsten like this one or something else, the atom in the middle is one net atom. But the corner atoms, as we talked about in lecture, are 1/8 in the cell and 7/8 outside the cell. So when it comes to net atoms per cell, each of the corner atoms is 1/8 inside the unit cell. And 1/8 times 8 is 1, plus the one atom in the middle, that body-centered atom in the middle. So that means there's going to be 2 atoms per BCC cell. cell. It doesn't matter if it's tungsten or any other atom, there's always going to be 2 atoms if it's BCC, if it's body-centered cubic. Finally, if the edge of the unit cell is 316.5 picometers, what's the radius of the tungsten atom? This is another important thing to know. In addition to knowing that BCC is 2 atoms per cell, you kind of also have to know the edge to radius ratios for these different unit cells. And if you look back in your notes, or you do remember, edge of a BCC equals 4 times the radius divided by the square root of 3. So since we have the edge and we want to find the radius, you want to take the edge, 316.5 picometers, multiply it by the square root of 3, and divide by 4. And that's exactly what we did right here. And if you did that correctly, 137.0 picometers. So when you hear BCC, all right, it's nice to know what it looks like, and there's a cool picture, okay? It's nice to know that there's 2 atoms per cell, and finally, it is nice to know the edge to radius ratio. I remember it as edge equals 4r divided by square root of 3, i.e. 4 times the radius divided by square root of 3, but you can do it radius equals square root of 3 times edge divided by 4 if you'd like to, no big deal. To summarize BCC, all right, 2 atoms per unit cell, radical 3 times the edge divided by 4 is the radius, or 4 times the radius divided by square root of 3 is the edge. Another thing I didn't mention, a picometer is 10 to the minus 12 meters, and we'll see some picometers in these problems. So just realize if you have to go from picometers to meters, there's 10 to the minus 12 meters per picometer. This is much smaller of a length than even the nanometers we looked at in Chem 221. Calcium crystallizes in a face-centered cubic cell. This is the FCC cell we looked at in lecture. The density of the solid is 1.54 grams per centimeter cubed. What's the radius of the calcium atom? Okay, on these kind of problems, all right, you either start at the radius and you go over essentially to number of atoms in a cell, or you can start with the number of atoms in the cell and go backwards to radius. And in the lab, we'll go through some examples of things like this. In a face-centered cubic cell, there's some stuff to know, just like the body-centered cubic cell we saw earlier. So for face-centered cubic cell, there are 4 atoms per cell, and the length of the cell equals 4 times the radius divided by the square root of 2, okay? So those 2 things are what you should know for FCC cells, and it doesn't matter what it is. So on this problem, there are different ways to do it, but I would probably start at 4 atoms per cell, and you can move from atoms to moles using Avogadro's. If you have moles, you can move moles to grams using the molar mass, because you know this is calcium, and we can look up calcium on the periodic table to find the grams per mole. Once you have mass, grams, you can turn it into volume using the density, the 1.54 grams per centimeter cube part. If you take the cube root of the volume, that'll lead you to the edge, which is what we have down there, and edge equals 4 times the radius divided by square root of 2. So the goal of this whole lab is just to find that radius value, that R part right there. And again, there's more than one way to do these problems. So here's what I did in this problem. I started really over here on the right, 4 atoms per cell. And there's always Avogadro's number of atoms per mole. So you can see how the atoms will cancel out, and you have now just moles. And this number here is the molar mass. If you multiply it by, the moles will cancel, and you have grams. And then finally, multiplying that by the density, the grams will cancel, and the only unit left standing will be the volume. This is the volume of the unit cell in centimeters cubed. And it's super small because unit cells, there's a whole bunch of them in any sample of thing. But from this volume, we can turn it into the edge length. Because these are all unit cells, length times width times height, they're all the same. So edge cubed equals volume. In this case, we want to go from volume back to edge. So this is where you get into what's called the cube root. The volume equals this number, and volume for these equals edge cubed. So we want to take the cubed root, and in your calculator, you might have this little symbol. It's like a square root sign, but it has a 3 next to it. That's called a cubed root, all right? And if you apply the cubed root to the volume, you should get 5.57 times 10 to the minus 8th. Now, if you don't see this on your calculator, don't panic, because there's another way to do these cubed roots. And honestly, we don't do them that much, but if we do, I want you to be prepared. You can also do a cubed root if you take 1.73 e minus 8. So that's 1.73 times 10 to the minus 8th. And the whole thing you want to raise to the power, that's the caret, all right? Raise to the power of 1 divided by 3 in parentheses. So 1.73 e minus 8 raised to the power of 1/3 is the same as a cubed root. And that should also get you there to the edge. Please practice this, all right? This is something that most people don't do a lot of, and it's just a math skill, right? It's not hard. This is a plug and chug, but it is something you'll have to do on occasion. So make sure you do it. Oh, and by the way, I just realized I was testing you, making sure you're awake. This shouldn't be minus 8. I was looking at answers. All right, that should be minus 22. Oh, bad instructor, sorry. 1.73 e minus 22 is what you'd want to have. I was looking at the answer, and I should have been looking at the 10 to the minus 22. Sorry about that. Anyway, back to your regular scheduled programming. Okay, so the edge length, the edge, 5.57 times 10 to the minus 8. And the edge equals 4 times the radius divided by the square root of 2. So if you want, what you can do is say radius equals square root of 2 times edge divided by 4, kind of like what we did in the last problem when we had, but it was for a BCC, not a FCC. But anyway, the answer comes out to be 1.97 times 10 to the minus 8 centimeters. Now, this problem doesn't really state to put it in a type of unit. Usually people will use angstroms, or more commonly probably picometers. So if you take the centimeters and you convert it over to picometers, it's 197 picometers. If you want to be really rebellious and use angstroms, go for it. That would be 1.97 angstroms, and any of these answers are fine. So this is a good problem. If you can do this problem, you've got all this material down, no big deal. Cool. Equilibrium vapor pressure for dichlorodimethylsilane, that weird compound right there, is given below, or pressures are given below. All right, first of all, what's the normal boiling point of dichlorodimethylsilane? Everything in B and C, honestly, is going to be a little weird, but I'm kind of hoping that everybody can at least get A, because a normal boiling point is where the vapor pressure equals 1 atmosphere. And if you look at those vapor pressure values, 1 atmosphere is 760 millimeters of mercury. So if the vapor pressure is 760 at this temperature, that means the compound is boiling. So 70.3 is the normal boiling point. That's where the vapor pressure equals the atmospheric pressure. The normal boiling point means 1 atmosphere, 760 millimeters of mercury. Boiling point, 70.3. The second part of this problem, B, it says plot these data as natural log of vapor pressure, which is what P is, versus 1 over T, okay? This is an example of what's called a Clausius-Clapeyron equation, and I do encourage you to check it out. When you plot 1 over T, do not use Celsius, all right? No, 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 don't use these values as is. You must turn them into Kelvin, all right? So when you're plotting natural log of vapor pressure, you can literally use these numbers right here. That's not bad. But when you do 1 over T, you first want to turn Celsius to Kelvin, and then go 1 over Kelvin. Kelvin. Okay, so Celsius to Kelvin, and then 1 over the Kelvin temperature is what the 1 over T is. If you've done this right, the natural log of vapor pressure versus 1 over the Kelvin temperature, you're going to see a straight line. And if you perform a linear regression analysis on the data, you're going to get the slope, the y-intercept, and also the correlation coefficient. So in this problem, here's what I did, all right? With a T minus 1, which is like 1 over temperature, it's 1 over the temperature in Kelvin. And that graph in the lower right is the result of my 1 over temperature in Kelvin versus and natural log of vapor pressure values. And you can see it's a nice straight line. It has a slope and a y-intercept, and I got these numbers from the linear regression. This is the correlation coefficient, another part of a successful linear regression. And if R is very close to -1, that means that your points align very well with the mathematically predicted line. It means you have good data. All right? R of -0.8 wouldn't be as good as an R of -0.9. All right, no big deal. It says in the part B, at what temperature does the liquid have an equilibrium vapor pressure of 250 millimeters of mercury? Okay. Oh, goodness. So what you want to do is you want to use this equation right here, and you want to put natural log of 250 in, and you want to solve for T minus 1, all right? And that's kind of a strange thing. I totally understand. So natural log of 250 equals -3885.2 times this T minus 1, T to the minus 1 power, plus 17.949. If you do this, T to the -1 comes out to be 0.00320. That's a 1 over Kelvin temperature. So if you take 1 over that number, it becomes the Kelvin temperature, T sub K, 312.6. And if you convert that into Celsius, 39 degrees Celsius is what I got when the vapor pressure is 250 millimeters of mercury. Now, let me just pause there for a second. Linear regression is a real powerful tool, and it does give equations like this. And why this is helpful is that you can see up there in the data, we didn't have a 250 millimeter of mercury vapor pressure to look at the corresponding temperature. However, using this equation, you can find the temperature for any vapor pressure you want. And that's a real powerful tool. You could also put in any temperature you want and figure out what the vapor pressure is going to be. So for a scientist, this equation is pretty cool. Clausius-Clapeyron is a little clunky at first to use, but it is just math, and I know you can do it. And of course, if you do have any questions, you be sure and let me know. Now, finally, calculate the molar enthalpy of vaporization for this compound using the Clausius-Clapeyron equation. All right? Well, if you look back in the notes at the Clausius-Clapeyron, the equation is natural log of P equals, parentheses, negative delta H vap over R times 1 over T plus C. How does that help us, Dr. Russell? Boy, that's a great question, and at this point, I'm not sure. No, I'm just joking. The slope, all right, the slope equals negative delta H vap over R. So if we can isolate delta H vap from that information, we're going to be good to go. So notice in the next part down here, I took the slope, and the slope is that negative 3885.2. That equals negative delta H over R. Now, R is the so-called energy R. It's an alternative version of R. We use 0.082057 a lot in the gases. This is the so-called energy R. The units are usually joules per mole Kelvin, but in this version, I'm using a kilojoules version because I want my answer to come out in kilojoules. Now, delta H vap is the heat of vaporization, the energy required to take a liquid and turn it into a gas. It's always a positive positive number. So if you get a negative number, something is wrong. Remember, there's a negative right there, and there's also a negative in our slope. So the negatives cancel. Delta H VAP, 32.3 kilojoules. Bam! This is how they get the heats of vaporization. So in some of those problems we did earlier, the Q equals MC delta T plus another mass times the heat of something. Well, this is how they calculate the heat of something. Clausius Clapeyron can be really cool for this kind of stuff. Okay, so that's it for Chemistry 222 problem set number 4, and I hope this has been a useful experience to you. If you have questions on the material after this, definitely check out the study guides and concept guides, which are located both on the website and in the companion. I also encourage you to check out the Guide to Intermolecular Forces handout, as well as the Cubic Unit Cells Guide for Metallic Solids handout. They will also help for particular parts of this problem set. And you can talk to the LSC/Avid Center, and you can talk to me, of course. Lots of opportunities are available for you. All right. Thank you for spending your time with me. I do appreciate it, and I hope this has been a useful experience. Good luck with your studying, and have a wonderful day.